Okay, then now we will start with the magnetostatics part. Till now in the previous lecture we have seen the static electric fields. Now we will come to the new topic where the magnetic fields which are independent of time. So we'll see what all the parameters come into picture. So but the basic thing is whatever the concepts we have studied in electrostatics, and that almost remains the same in magnetostatics also. So the way how we have proceeded there, starting with Coulomb's law, electric field intensity, electric potential. So all those concepts remain same. In the same manner, we will try to follow in magnetostatics also. So similar to the Coulomb's law, that what we have discussed in electrostatics, and here we have the equivalent is Biot Savart's law. So you might have been known about the Biot Savart's law. So what the Biot Savart's law says, if we have any current carrying element, let us say this is my current carrying element, and I was passing a current of I amperes. So in our physics we have studied every current carrying element is going to create a magnetic field. So when you see the analogy between in electrostatics, every point charge can create an electric field, and similarly every current carrying element is going to create a magnetic field. Now this is the position where I want to define how much field is existing at this point. So the measure of this magnetic field at this point is given by the magnetic field intensity. So similarly in electrostatics we have studied. So wherever you are finding the electric field intensity, that is the measure of how much field is at that point. So if you see the same comparison, so every current carrying element is going to create a magnetic field. So the magnetic field intensity at this point is basically given by the Biot-Savart's law. But you have to keep it in mind, the Biot-Savart's law gives the magnetic field at this point due to a small current element. That means it will not give the magnetic field here due to the entire wire. You take a small portion of the wire. So I can call this as a differential length dl. So the Biot-Savart's law gives the differential magnetic field due to this current element. So first of all, the terminology how to understand. What do you mean by current element? So the current element is nothing but the current I flowing in a differential length of dl. So it's not the total wire, it's a small portion or the section of the wire which is carrying the current I. So next time also I will use the same terminology, so you should remember. So the current element means current I in a small differential length of dl. So this is your source right now, the carrying element, and this is your observer where you are finding the magnetic field. Now what the Biot-Savart's law says, the differential magnetic field intensity at this position is equal to the current element into sine of angle divided by 4 pi r square. So it is directly proportional to the current passing through this element and is inversely proportional to square of the distance between them. So this is a differential magnetic field due to a this is the differential magnetic field due to the small current element. So this magnetic field intensity is basically a vector. So can you tell me what is the unit of this magnetic field intensity? So please reply in the chat box. What will be the units of magnetic field intensity? You can see this here only. Exactly. Here you can see current is in amperes and this differential length is in meter and r square is in meter square. So ampere meter divided by meter square. So you are going to get the units of ampere per meter. So sin theta is a constant. So for the better understanding, I will rearrange this equation in terms of the vector. You know that this differential magnetic field is a vector. So I will try to write the differential magnetic field with the cross product of the current element into the radial direction divided by 4 pi r square. So the same equation, instead of writing in sign of angle, I will mention it as some cross product of two vectors. So even if we know the cross product, what is the definition for cross product? So a bar cross b bar is equal to ab sine theta. So in your case, a bar is nothing but dl. So you can see here, and b bar is nothing but modulus of unit vector. You can see here, modulus of unit vector is 1 into sine theta. So whatever dl into sine theta, I have written as the cross product of dl vector into the unit vector along this, the vector r bar. So you can remember this equation, or otherwise I feel this is much better to remember when you go for the problems, because straight away this equation gives the direction of the magnetic field intensity also. So you try to remember this formula. So the differential magnetic field is equal to the current element ideal cross product with the unit vector along the radial direction, that is a radial cap, divided by 4 pi r square. Now I want to find the total magnetic field due to the entire length of the wire. So let us say L is the length of the wire. So to find out the total magnetic field intensity, you need to integrate the differential magnetic field from 0 to L. So which means integral 0 to L ideal cross AR cap by 4 pi r square. This gives the total magnetic field due to the entire length of the wire. So the Biot Law is basically gives the differential magnetic field. So to find out the total magnetic field, you can integrate straight away. And here the units of the magnetic field intensity will be in the order of ampere per meter. So any doubts in this slide you can ask. The direction of cross product. Okay, next part is that only. I will discuss the direction part now here. See, the direction of the magnetic field intensity you have already studied in physics. The magnetic field intensity direction is basically given by the Fleming's right hand principle. So first I will discuss the Fleming right hand principle, and after that I will tell you one more technique to find out the magnetic field intensity direction. So two methods I am going to discuss. So the first method, you can see here, this is your current carrying element. So the current is flowing in the upward direction. So you can start with your right hand and make sure that this thumb is pointing in the same direction of current. So when you start with your right hand and placing the thumb in the same direction of current, what is the encircle movement of these fingers? So what about the other fingers? How it is getting encircled? So or you can say it's the locus of the movement of the other fingers. So the encircle movement of the other finger shows the direction of magnetic field. So start with your right hand by making the thumb in the same direction of current and find the movement of all other fingers. So the movement of other fingers shows the direction of magnetic field. So for example, I will give you one thing here. One example, you can tell me. So suppose there is a current carrying element which is located along Z direction. Can you tell me what is the direction of magnetic field? You can reply in the chat box. So I have placed a current carrying wire and the current is passing in the positive Z direction. So you start with your right hand, make sure that the thumb lies in the positive Z. And what is the locus of other finger shows? What is the encircle in XY plane? Can you be specific? So when you place the thumb in the Z direction, so your encircle movement of all other fingers shows in a circular fashion, right? Somebody is saying rho. Is it correct? So this is your Z axis. You need to complete the locus of all other fingers. You need to make a complete rotation. So when you make a complete rotation, it will be in the anti-clockwise. Correct. So can you tell me what direction it is? When you move around Z, what is going to change? Exactly. Phi direction. So the moment once you place a current in the Z axis, you are going to create a flux in the phi direction. Because when you are moving around Z axis, your rho always remains same. You have to remember that point. So when you are moving around the Z axis, only there is a change in the azimuthal plane. So that's what we have seen in the cylindrical system. So in this case, since the current is flowing in the Z direction, the magnetic field will be created in the phi direction. But again, in most of the questions, they will be specific about a particular point. So that case also we will see when the observer is there. So in this case, first of all, the direction of magnetic field will be in phi direction. Okay, this method is clear for all of you. Fleming's right hand rule. So once this method is clear, I will try to tell you the second method. So uh, first give me the clarity that whether you have understood or not this method. In reply. Okay, we'll see the second method right now because both the methods you have to remember. So at one point, the Fleming right-hand principle is going to be more useful rather than the shortcut. At some other point, this whatever the method I was going to discuss is more helpful. So both the methods you need to be able to understand. So the second method was, I will tell you a simple shortcut you can write down. The direction of the magnetic field is the cross product of current element direction into radial direction. So if you want to find the magnetic field direction, it is the cross product of current element in which direction the current element has been placed and what will be the radial direction. So because I was doing the same thing with the Biot-Savart Law itself, you can see this equation. So when you see the equation, the magnetic field is the cross product of current into radial direction. So I was going to make use of that definition. So try to apply the same shortcut in this same example. So if the wire is located along the axis, so what is the current element direction here? So this is located along Z axis. And what do you mean by radial direction? So this is your Z axis. So for Z axis, which movement represents radially away from Z axis? Radial means you are moving radially away from Z axis. So when you are moving away from Z axis, which component is going to vary? Can you reply? So the moment once you are radially moving away from Z axis, which component is going to vary? Exactly, correct. So your rho will vary, right? So the radial direction represents the perpendicular direction from the source. So since line charge is, current is located along Z axis, radial direction is rho. So what is AZ cross A rho here? This will be A phi. So you can see here both the things, either you can apply the Fleming's right hand rule or the second method. So both has been given the same answers. So I will summarize again. So using your Fleming's right hand principle, make the thumb in the, you start with your right hand by placing the thumb in the same direction of current and see the movement of all other fingers. That gives the direction of magnetic field. That is the first method. And the second method is the direction of magnetic field is the cross product of current element into radial direction. So this is straight away gives the magnetic field direction. So let me give another example here. See here, this is my z-axis. So where the current is flowing right now, and this is my observer position, right? So when you consider at this observer position, what will be the direction of magnetic field? Is it outside the plane of the board or into the plane? When you consider at point A, what will happen? You start with your right hand as shown here. You place it in the same direction of current. So at this point, when you consider at this particular point, all other fingers shows outside the plane, right? So that is the reason why I have represented with a outside plane. Whereas the moment once you reach the B, that means you are closing your fingers all together. That means when you are closing the fingers, by the time you reach B, your fingers are pointing into the plane of the paper. I hope you understood, right? So at point E, your fingers are pointing outside, and at point B, your fingers are pointing inside. So this is an example where you can clearly see how the Fleming's right hand rule can be applied. Okay, is it clear? So at point A, the fingers are pointing outside the plane, and at point B, all your fingers are pointing inside the plane of the paper. So you got the point here, the direction of magnetic field intensity. Right. So the magnetic field intensity is just only the measure of how much magnetic field is existing at a particular point. So in order to define the magnetic field intensity, you can make use of the Biot Savart's law. So the Biot Savart's law gives the differential magnetic field due to a small current element, and you can integrate the differential magnetic field to get the total magnetic field due to the full length of the wire. So that is a concept you have seen till now. And next thing what we are going to discuss is a new topic that is called a magnetic flux density. So to understand about the magnetic flux density, here I have considered a permanent magnet. So when you consider a permanent magnet, it is having a north pole and it is having a south pole. So what will happen when you consider any magnet? So there will be a magnetic flux lines which will be originating from the north pole and ending towards the south pole like this. So it starts from the north pole and making a loop, and the magnetic flux lines are terminated at the south pole. So this is a physics behind the magnetic fields, right? So the magnetic flux lines start from north pole and ending towards the south pole. So you have so many flux lines that I have shown here like this. Now I have considered a small differential surface here. This is a surface which I have considered. So the magnetic flux density represents how much magnetic field or the magnetic flux is passing through this surface divided by the area of this particular surface. So you consider a small surface, you see how much magnetic flux is passing through that. So mathematically, if I want to write, the symbol for defining the magnetic flux density is nothing but B. So I can say the magnetic flux density is the magnetic flux passing through a given area. So you consider a small surface, how much magnetic flux is passing through this surface is a measure of the magnetic flux density. So can you tell me the units of this? What is the unit of magnetic flux density? Ampere per meter cube. How it came? Ampere per meter cube. First of all, what is the unit of magnetic flux? At least try to answer me. What is the unit of electric flux? Did you remember? What is the unit of electric flux? Correct. At least I am happy now. You have remembered that. So similarly, the unit of magnetic flux is what? What you have studied in your BE? Yes, correct. Webers. So the magnetic flux can be measured in the order of Weber. So the unit of magnetic flux density will be Weber per meter square. This is also called as Tesla. Or sometimes there is another unit for magnetic flux density. It is measured in the order of Gauss. So I was giving the relation here. 1 Tesla is basically same as 1 Weber per meter square is same as 10 power 4 Gauss. So this is the relation between all these three. You can remember this. So 1 Tesla is 1 Weber per meter square is same as 10 power 4 Gauss. That is a conversion. Now it's the reverse. If we know the magnetic flux density, how will you calculate the magnetic flux? So the magnetic flux through any surface is mathematically given by, I can define with a symbol phi is equal to the magnetic flux density multiplied by the area. So if the surface is nonlinear, you can do the integration. So the magnetic flux density is equal to double integral B dot ds. So any questions in the magnetic flux density? Okay. So next thing is similar. We have seen there the relation between the electric flux density and the electric field intensity. So that is D is equal to epsilon times E. Similarly, the magnetic field intensity and the magnetic flux density both are related by, you know the relation already, B is equal to mu into H. So B is in the order of Weber per meter square and H is in the order of ampere per meter, and mu is basically said to be the permeability. So mu is nothing but the permeability of the medium. So mu is related as mu naught into mu r, and mu naught is said to be the free space permeability, and mu r is basically said to be relative permeability. So the free space permeability value will be 4 pi into 10 power minus 7. So can anybody tell the unit of this? What is the unit of permeability? Nobody? So the permeability is in the order of Henry per meter. So the same thing, whatever we studied in your electrostatics, same thing is there. So let me make a comparison, then you will understand it better. So I will try to compare the static electric field versus the static magnetic field, right? If you see the similarity in electrostatics, we have started with the Coulomb's law, right? And the equivalent what we have started in magnetostatics is the Biot-Savart's law. And the second comparison is from the Coulomb's law, you are able to define what is the electric field intensity. Similarly, using Biot-Savart's law, you are able to define what is the magnetic field intensity. The third point, the direction of electric field intensity is radially away from the source or radially towards the source. But ultimately, it will be radially away or towards the source. It's a radial direction. Electric field direction will be. So the direction of magnetic field will be basically the cross product of current direction into the radial direction. And similarly, there also we have seen the concept of electric flux density. So here the equivalent will be the magnetic flux density. So I have defined there D is equal to epsilon times E. So similarly, the magnetic flux density is nothing but mu into H. And the next comparison, there the permittivity of the medium will come into picture. That is equal to epsilon naught into epsilon r. Similarly, here permeability of the material is coming into picture. Mu naught into mu r. So mu naught is basically called the permeability and epsilon naught is the permittivity. So in the electrostatics part, I have given the definition for permittivity, right? So what is the meaning of permittivity was the ability of the medium to allow the electric field that I already told you. Similarly, what is the permeability represents? So the permeability is the measure of the capability of the medium to withstand the magnetic fields. So if any medium is having high permeability means it can easily allow the magnetic field through that medium, or you can say it can easily store the magnetic field in that particular medium. Is it clear? And the unit of permittivity, there you have seen farads per meter, capacitance per unit length. And similarly, the permeability units will be Henry per meter, inductance per unit length. Okay, to understand these concepts better, I will try to ask one more question. So the first question is, so this is out of the discussion I was discussing. I hope it will be fine. So this is very important even if you go for the interviews, these kind of questions. So let's concentrate on this question carefully. Suppose when I am talking about an electromagnetic waves, all those electromagnetic waves are propagating in the free space. So the question here is, you are not feeling the sense of the electromagnetic waves which are propagating in the free space. Consider the other way where you have a conductor and I applied a voltage across a conductor. The moment once the voltage is applied, there will be a current flow through this conductor. And the moment once you are standing here and you are able to touch this conductor where there is a current flow and your body is grounded. In that case, what will happen? You are going to get a shock because you are going to touch a conducting plate and your body is grounded. So there will be some amount of current will flow through your body. There will be some potential differences develop and you are able to feel the sense of the current. So why don't you apply the same logic in the free space? So when you touch a conductor, you are able to feel the sense of it. But whereas all the electromagnetic waves are propagating in free space, and still you are not going to get the sense of that. You are not feeling that some kind of waves are traveling surrounding you. So you are not able to get that sense. So can you tell me the answers now? Now the options is open for all. So please try to tell me the answers. What do you think will be the reason here? You can speak out. Don't waste the time in doing chatting. Yeah, you can speak out here. The option is open for all of you. One by one, you can speak, no problem. Whether it is correct or not, also it doesn't matter. So you can share what is your, what do you think? You people can share, no issue. Whether it is right or not, it's not a problem. Whatever you think, you try to share. First of all, is the question clear for everyone?
So,
Yeah.
what I think is that like electric field is like the force experienced. So probably the force which we are experiencing is very negligible. But then like when you touch the conductor, it's like the flow of electrons. So like the flow of electrons through the body is deemed as shock. But then electric field is a force which is very negligible.
Okay. Okay. How in what comparison you made like how the electric force is negligible?
I was just trying to make a thing. Probably it's negligible. Maybe that's why we are not feeling it. Just a guess.
Okay, but quantitatively, how you are not sure that how much force can be existing, right? It's a just
Yeah.
assumption that the force is negligible.
Yeah.
Okay, others? So first of all, the thing was when an electromagnetic waves are propagating in the free space, the conductivity of the free space will be zero. This is the major dominant term here, which is going to feel the sense. So if any particular medium is having a conductivity means it will support the flow of current. So generally in your EDC also you would have been studied, a metal is a good conductor. Means that when you apply any voltage across a metal, there will be a current flow. So whenever there will be any current flow and if you are touching that metal, you will get a shock because the current is the reason. And ultimately this current is due to the conductivity of the medium. So when you consider in free space, the conductivity of the free space will be zero. What it means? There is no information of the wave in the form of current. So when I say an electromagnetic wave, the information is in the form of electric field and magnetic field, and there is no more current exists in free space. And you will get the sense whenever there is a current flow. So the basic reason why you are not getting the shock was the conductivity of the free space is zero, which means that there is no current flow in free space. And it is horrible to imagine once the free space is conducting, all your communication is revolving around that. So whether it is a satellite communication or radar communication, you are choosing the free space as a medium. The reason was your conductivity is zero, and hence we are safe. So you just imagine what will happen if the free space starts conducting. So it's a miserable thing, right? So the main thing what is causing this is that the advantage of free space is that for all your communication you are using free space as a medium, because our human beings will not get influenced by the electromagnetic radiation, because it doesn't carry the information in the form of current. So is it make sense? Can you repeat the last point which is missed? So the point is very clear. The conductivity is a major thing which will define whether you will get affected because of that or not. In free space, the free space or the air, which doesn't, the conductivity of the free space is zero, which means that there is no information flow in the form of current. So in case of a free space, all the electromagnetic waves are carrying the necessary information. That means all the information is in the form of electric field and magnetic field. So whereas when you consider this case metal, so the flow of information is carrying in the form of current. So the current is existing because the metal is having the conductivity. So if you consider fully, if you consider any medium, I can summarize it right now. Electrically, it is characterized by three parameters. So one is the conductivity, and the other one is the permeability, and the third one is the permittivity. These three are the material constants which will be electrically defines the parameters of the material. So the first one is the conductivity. So if I want to define what is the conductivity, the ability of the medium to withstand the current is nothing but the conductivity. So for example, the metals are having a higher conductivity, which means that the metals is going to support a huge value of the current. So the property of the conductivity defines whether that medium is able to allow the current or not. So more conductivity means more current, and less conductivity means there is no current, like that. So similarly, the permeability, just now I have seen. The permeability represents how easily the medium is allowing the magnetic field. The simple example, first of all, the simple example for good conductor is nothing but all your metal or high conductivity. So similarly, if you consider the mediums or materials which are having high permeability, is nothing but all your transformers. If you see in the outside all the transformers, which will be made up of iron core. So the iron, or you can say the steel or mu metal, all these materials is having a high permeable materials. So suppose if you take the transformer example, the transformer has to be designed to withstand the more magnetic field. The funda of transformer, right? So first of all, material should be able to support more magnetic field. So that is the reason why the iron is more frequently used in the transformers. So different kind of compositions, it will be laminated iron core, different kind of core shapes will be available. So that is a permeability. And the permittivity means the ability of the medium to allow the electric field. The simple example for permittivity is our human body itself is having a higher permittivity. I can justify with one statement. Suppose if you get sick and if you go to doctor and he is advising you to get diagnosed, okay. So if there is any part which is get damaged in your body, so the doctor is going to pass an X-ray signal through your body, and with the help of X-rays, he will be able to analyze what is happening there. So X-rays are basically nothing but a high strength of field. So why he is using the X-rays was because your body can easily allow the electric field. So as a result, these X-rays can penetrate through your body and thus he will be able to analyze so which part has got damaged. So the simple example for the permittivity is nothing but our human body itself. And there is one more thing is there, our human body permittivity is in turn a function of frequency. So there are a few certain materials where the permittivity will be constant. But when you see the characteristics of the human body, the permittivity is basically a function of frequency. So you can ask me the same question where why he is passing the X-rays, why can't he pass a signal in the range of megahertz? X-rays are basically, when you consider X-rays, typically in the frequency range of 10 power 20 hertz. So you may have a question that why only the specific X-rays will be required to diagnose it, for the diagnosing purpose. The reason was I told you, right, the human body permittivity is a peculiar thing and which will be directly proportional to the frequency. So when you pass a megahertz signal frequency through your body, your permittivity is less, which means that that megahertz signal is going to incident on your body and it will not penetrate, rather it will get reflected back. So if it is not penetrating through your body, you cannot analyze what happened in your case. So in order to correctly diagnose the problem, he is going to use a higher frequency X-rays. So your body can easily allow that and you will be able to identify the problem. So this is how all the materials are characterized. One will be the conductivity, permeability and permittivity. So is it clear? Any questions you have? So you can ask any questions or otherwise you can reply in the chat box. Good. So we'll go back to our presentation. We have deviated completely. So we're in this slide. So the magnetic flux density is nothing but B is equal to mu into H, and mu is nothing but mu naught times mu r, and mu naught is the free space permeability. So that value is given here, and mu r is the relative permeability. And the next thing what we'll try to understand is the types of the current distributions. So similar to the type of charges there you have seen point charge, line charge, surface charge and volume charge. Similarly, there are a different type of current distributions. So one type of current distribution we already seen, that is a line current. So I don't want to discuss much about that. Line current means the current is passing through a small thin wire which is negligible in thickness. So all your current carrying wire, that example is copper wire, is an example of a line current. So that is very clear. And the other kind of configuration is the surface current, as you can see in this diagram. So the surface current, before discussing this, I will try to give an example for this. So assume that this is a metal sheet and I was going to apply a voltage across this. So based on the voltage and the conductivity of this metal, and there is a current flow. And that current flow this time is along the surface, right? So that is an example of your surface current. So when you apply any voltage across a metal, which consider that the thickness is negligible, and so there will be a current which will be flowing on the surface of the metal, that distribution is considered as a surface current. So in case of a surface current, instead of mentioning the current, there is one more parameter which will characterize it as the surface current density. So the surface current density is basically defined with a symbol K. So the definition for surface current density was the current divided by the area. So you can see the same comparison what we have studied in electrostatics. So the surface charge density will be the charge per area. So the charge is same as current element here, as I mentioned. So what will be the current element I have discussed when I was discussing about Biotsavart Law. The current element is the current flowing in a differential length. So a simple example is current element is I into dl. So in this case, so let me consider this is your x-axis and this is your y-axis. And I have considered a small part of the metal, or you can say small part of the area. In this case, what will be the current element? Can you tell me? Is it I into delta X or I into delta Y? So I have taken a small part here and I was trying to write the current element here. Is it I into delta X or I into delta Y? Delta X, correct. Because the current element, this DL should be considered in the same direction of current. So in this example, I have considered there is a current flow which is happening along the X direction. So the current element will be defined as the small amount of current delta I. I was telling because I have taken a small loop which will not give the total amount of current. So I have taken the differential current is delta I in a length of delta X divided by delta X into delta Y. Because this area, if we calculate, length is delta X and area will be delta Y. So if we are calculating, the current density can be written as delta I divided by delta Y. And what will be the unit of K right now? Surface current is same as your ampere per meter. Most of the people are expecting that it should be ampere per meter square. That is wrong. Whereas surface charge you have seen it is coulomb per meter square because it is charge per area. But whereas in the same way, if you are thinking the surface current density has to be ampere per meter square. But the reason was here current is not the reference, your current element is the reference. So the current element means the current delta I into delta X divided by area. So you are going to get the surface current density same as your magnetic field intensity. So the units of surface current density is very important. It is ampere per meter. Though it represents a surface, the units will be ampere per meter only. Now, in this case, so let me write delta I value right now. It will be K into delta Y. To use this same equation and rearrange that. And what will be the total current if I want to find out in the entire loop? I have to do a single line integral K into delta Y, where Y limits is varying from 0 to B. So you have to take the limits of Y. So this gives the total current enclosed in the loop. So first of all, the surface current density is basically defined as current element per area. So the current element is considered in this case as delta I into delta X divided by area is delta X delta Y. So once you know the surface current, to find out the total current, you need to do the single line integral in a Y direction. Is it clear? Surface current? Yeah. Let me give an example for this. So assume that there is a sheet of current which is located in an YZ plane. This is located in an YZ plane and the sheet is having a dimensions of 10 meters along Y direction and 5 meters along Z direction. And the current is flowing in this direction. And the current density I have given it as 20 ampere per meter. So you know what is the definition for current density right now? Considering the current density, I want what is the total current enclosed in the entire sheet. How much total current is carried by the entire sheet? What will be the answer? So you can try to do the calculation and tell me the answer. Is it 200 or 100? 100. Why it is 100? K into 10. Exactly. I have seen in the previous case also, the value of I is nothing but the line integral of K into delta Y. So always you have to integrate the surface current where the limits, whatever the limits you are applying here, that should be perpendicular to the current, right? So in this case, I already told you, in this case, current is flowing in. Again, go back to the basic definition. The current element is delta I delta X into divided by surface area will be delta X into delta Y, right? In this case, your delta X term gets cancelled. So to find out the total current, you have to integrate the surface current with in a direction which is perpendicular to that. Here, if you see here, current is flowing in the X direction. But while applying the limits here, you are applying the perpendicular. Because already that X direction gets cancelled in the definition. And I hope you understood here. So in this case, the current is nothing but the current density multiplied by some length. This length will be perpendicular to the current. So here the current is flowing along Z direction. So you should not multiply the Z component. You should multiply with a component which is perpendicular to K. You should multiply with 10 right now. So the answer will be 20 into 10. That is nothing but 200 amps. So I hope it is clear for everyone, right? So this is very important because whatever I have seen till now in the students was they will be comfortable in doing the problems of electrostatics. And once it comes to the magnetostatics, I don't know the reason, they will think that it is a very complicated subject. But here, that is the reason why I was asking you at any point, if you are not able to get the concept and try to ask one more time, I will be ready to explain one more time also. So please get all the concepts, get it clear. So, and it is very important for you to understand the magnetic statics. Actually, if you are seeing it, it is really interesting. The magnetostatics part, if you ask me. Anyhow, this concept is clear, right? Surface current. Shall I move on to the volumetric current now? Right. So volumetric current means the simple here you can see here in the diagram. So this is assume that this is a current carrying conductor. So when you apply voltage across this conductor and this time the conductor is fully densed. So the current is flowing randomly like this. So the current is flowing through the entire volume of this conductor. So that is the reason why the current is distributed in a volume. So I have characterized it as a volume current. Because here the current is not flowing in a line and not flowing along a surface, where the current is flowing in the entire volume of this conductor. So the full volume of the conductor is occupied by the current. So I called it as a volumetric current. The simplest example is nothing but a current carrying wire with a considerable thickness. If the thickness of the wire is huge, you can say that the current is distributed in the full volume of the conductor. So that is an example of the volumetric current. So to define the volume current density, so same procedure we will apply. So the volume current density, this you have studied in your EDC, that is basically called J, is nothing but same as the current element divided by the volume. So surface current we have defined it as current element per area. So volume current density is defined as current element per volume. And assume that the surface current density lies along x direction. For an example, so let me consider you have a parallelogram something like this, and this is your x-axis, and this is your y-axis, and this is your z-axis. And the current density lies in the x direction, and it occupies the entire volume. Now, how to find the current element in that case now? So the current element is defined as, you take a small parallelogram here, and the current element means the small amount of the current in a length of delta x here, because as I mentioned, current density lies along x direction. So delta I into delta x divided by, what is the volume of this entire cuboid or parallelogram, you can say, that will be delta x delta y into delta z. So your delta x gets cancelled, so that will be delta I into divided by delta y into delta z. So if you see the unit of volumetric current density, this will be ampere per meter into meter. So you can say ampere per meter square. So to find out the delta I current, that means if you take a small surface here, the current enclosed within this area is nothing but, you can see this equation, delta I can be obtained by multiplying J with delta Y delta Z. So J into delta Y delta Z. So what is the current I here right now? I can say that is double integral J into delta Y delta Z. So Y limits, if you say ABC is the units, A is the length and B is the width and C is the height. So in that case, you can say 0 to B and 0 to C. So this gives the total current enclosed by this full surface. So or in other words, you can say that the current can also be written as double integral of J into surface area. This surface area, how we have to choose was, suppose if the current density lies in the x direction, this surface you have to choose it in the YZ plane. Similarly, in the previous case, we have seen I is equal to integral k into dy. So this dy limit should be perpendicular to direction of. Similarly, if we know the volumetric current density, to find out the total current, so that is the double integral of j dot ds. So if the current density lies in x direction, you should consider a plane in the yz plane for the integration. So same as that, because your delta x component gets cancelled here. So finally, what is the summary here? In terms of line current, the value will be I, and in terms of surface current, you will get the line integral of K into some delta Y or delta L. But remember, this limit should be selected which is perpendicular to the current. So in terms of volumetric, that is double integral J into delta S. If suppose J lies in the direction of X, so this delta X is nothing but the YZ plane. Suppose J lies in Z direction, this differential surface will be dx into dy, like that. So the current is in the order of amperes and the surface current is in the order of ampere per meter and the volumetric current lies in the order of ampere per meter square. So any questions in the current distribution we can discuss. So the concepts are clear now. Shall I move? Shall I go ahead? So next we will discuss about the Maxwell's equations. So we have seen two Maxwell's equation for static electric fields, and now we will see the same kind of Maxwell's equation for magnetic. Okay, we'll see the Maxwell's equations for the static magnetic fields part. So this also will try to simplify it as simple as possible. So for that, if we see the nature of the magnetic flux lines we have studied. So if we have a magnet, the magnetic flux lines are said to be rotational in nature. So what is the meaning of that? So when you consider any magnetic field vector, whether it is a flux density or field intensity, the magnetic flux lines are always rotational in nature. Or in other words, there is no divergence nature exists for magnetic fields. Is my statement correct? If we consider any source of magnetic field, all the magnetic flux lines should be form a closed line, which will be rotational. So there is no divergence nature which will exist for magnetic fields. So will you agree with my statement? Yes. So if there is no divergent nature exists for magnetic field means the divergence of that vector must be zero. So this is your first Maxwell equation. No need of any full derivation kind of parts and all. So with the help of simple physics, we can say that all the magnetic flux lines are said to be rotational in nature, or there is no divergence nature exists for magnetic fields. So the divergence of the magnetic flux density or the field intensity, whatever you consider, that should be zero. So this is your first equation. So let us try to put the same Maxwell equation in terms of integral form. So for that, what I will try to do, I will multiply both the sides with a finite volume. So anyhow, right side will be 0, and this equation I will try to put it in this form. So triple integral del dot B into dV is equal to 0. So right now, using your divergence theorem, what you can say, the volume integral can be converted back into closed surface. Because what the divergence theorem says, every closed surface is associated with a finite volume. So the volume integral is converted back to surface integral, something like this, double integral b dot ds, provided the surface has to be closed. That will be equal to 0. So this is a Maxwell's equation in integral form. So the first thing is there is no divergence nature exists for the magnetic field. So your del dot B is equal to 0. And the same thing if you rearrange with some mathematical manipulation, you will get this. So double integral P dot ds is equals to 0. So what is the meaning of this one? You try to understand. So when I was discussing about the magnetic flux density, I told you one equation. The magnetic flux passing through any area is nothing but double integral B dot ds. Now what is this condition says? So whenever the surface is closed, the magnetic flux leaving the surface is equal to 0. That is what this equation says. So what is the meaning of that? Let me explain it again. So this is your magnet, right? And I was trying to enclose this magnet with this closed surface, something like this. Now, when I consider what is the net magnetic field which is coming out of this surface, the Maxwell equation says that the double integral of B dot ds is equals to 0. That's what it says. As per the Maxwell equation, right? So let me explain it in a different way. So the total magnetic flux you can see here, I can consider it as the flux coming from North Pole as well as the South Pole. Because North Pole is one source of magnetic field and the South Pole is another source of magnetic field. So I can say the total flux due to any magnet is the magnetic field due to North Pole plus magnetic field due to South Pole. So what happened in this case, whatever the flux generating from the North Pole, the same thing is entering into the South Pole. So for an example, if I say 10 Webers of the flux is coming out of the North Pole means the same is entering the South Pole. So what is the meaning of that? If 10 Webers is leaving the North Pole, the same 10 Webers is entering the South Pole. So why I have written minus, you would have been understood. Because from the North Pole, the flux is leaving and for the South Pole, it is entering. So what is the meaning of the total flux right now? It is 0. So the moment once the surface is closed, you are able to capture the flux generated from the North Pole as well as the South Pole. Since the same flux is developed or generated from the North Pole and it is entering the South Pole, the net magnetic flux will be 0. The net magnetic flux means double integral B dot ds. When the surface is closed, that value is equal to 0. So this equation also says that the magnetic monopoles will never exist. This is a very important statement. So this Maxwell equation also justify that there are no more magnetic monopoles. That's what we have seen. So suppose you assume that there is only a magnetic monopole. That means only the North Pole is existing. In that case, can you get the value of phi is equal to 0? Can you answer? Suppose if I have only a magnet where only the North Pole is existing. Can you get in that time the flux will be 0?
No, sir.
Right. So which means that the flux gets zero because there is one source which is generating the flux and there is one other source which will be absorbing that. So that I can call it as north pole as a source and south pole as a sink. So when you consider the magnetic field, the one which is generating the magnetic flux, you can call it as a source. And the one which is absorbing the flux is nothing but sink. So in other words, if you take any magnet and you cut it into small partitions, each small partition will also have one north pole and one south pole. So it doesn't matter whatever the size of the partition you make, in how many number of partitions you make also, you cannot be able to isolate the north pole and south pole. That's what it says. So even this equation also says that the flux becoming zero because there will be source and sink exist together. So that is the reason why, in other words, I can say the magnetic monopoles will not exist. So the first Maxwell equation you understood? Not only the magnet, you remember, it's not only the magnet. You take any current carrying element which will generate a magnetic field and you try to enclose the source with a closed surface. So the net magnetic flux leaving the closed surface will always be zero. So do you remember what will be the net electric flux leaving the closed surface? If it is electric flux, what will be the net electric flux leaving the closed surface? Q. Good. That's what we have seen right in Gauss law. So whatever we have studied in electrostatics, full opposite here. So in electrostatics, what you have studied, the curl of the electric field is zero. That's what you have studied. Whereas in magnetic field, you are getting divergence is zero. And there what it says, when any charged particle is enclosed with a closed surface, that net flux is equal to charge present inside it. Whereas here, when you take any source of magnetic field and try to enclose with a closed surface, the net magnetic flux will be zero. Right? So it's quite exactly opposite, you can say. So the first Maxwell equation says that there is no divergent nature exists for magnetic fields, or in other words, the net magnetic flux leaving a closed surface is always zero. Magnetic flux lines here will lie in the same plane of the bar magnet. It doesn't matter. It doesn't matter. It need not be lies in the same plane of the bar magnet. See here, the magnetic flux will be generating and it can occupy two or three planes together. But the moment once the surface is closed means it is able to cover all the planes. So in that case, it will be zero only, right? Yeah. So we'll try to discuss the next Maxwell equation. This is also simple. And assume that this is your current carrying wire. And as I said in the Fleming's right hand principle, when you place the right hand thumb in the same direction of current, there will be a magnetic field which will be developed in this direction. Now, what I will try to do, I will try to integrate the magnetic field intensity over this particular loop. What is the value of this? So a current carrying element is going to create a magnetic field. I was integrating the magnetic field in this particular loop. What will happen right now? So if you see the unit wise, this particular term gives something like this. The magnetic field intensity, it is in the order of ampere per meter and the length will be into meter. So finally the answer is going to be in the order of amperes. Right? Now I want exactly what is that current. Is it less than I or greater than I or it is exactly equal to I? Can you answer? It is equal to I. What is the reason?
Because it's the same loop, sir.
Means I didn't get you.
Because current through the loop will be always same, means it will not change in one loop.
What is the meaning of that was, see, suppose if we have a current carrying element, you know that the magnetic flux is developed in all the direction, and you have taken the line integral also, the full line integral. You have not taken a small part of something like this. You have taken a loop which is already closed. That means you are able to capture the magnetic flux one time, right? So since the magnetic flux is completely captured, this is exactly equal to I. Suppose if we have a current carrying wire here and you taken only this particular surface. In this case, your loop is not closed, which means that your current will be less than I. Right. Now, by applying the same logic, suppose this is my current and this, let us say this is carrying a current of 10 amperes, and I have surrounded this wire with 4 number of windings. So let us consider this is A and this is B. So what is the integration of H dot dl when you are doing it from A to B? Can you tell me what is the answer? This loop is having 4 windings and the current passing through the wire is 10 ampere. So what will be the value of this line integral? You can reply the answer. $40. Others? Is it 40 or 10?
10 for each loop. 4
Yeah.
loops 40.
Exactly. So do you mean that that 40 amperes of the current is exactly flowing through the wire?
No, sir.
So what is the meaning of that? The answer is 40 ampere is correct, but people will take it in a different way. I was passing only a 10 ampere current. How will be able to capture the 40 amperes of the current? Can you justify?
No, sir.
Yeah, the actual current passing through the wire is 10 ampere, but right now if you are getting it here, you are going to get a 40 ampere current. How can you justify that? So let me give you a simple example for that. It's the meaning is not that actually. You are not able to capture 40 ampere. See, as per the Ampere's law, what it says, when you consider a single loop and this is your 10 ampere, so the line integral of H dot dl will be straight away 10 ampere. So what is this meaning says was, you are going to capture a magnetic field which is corresponding to a current of 10 ampere. Right. Now in the same fashion, the same current carrying wire is enclosed by 4 number of windings and you are doing the integration from A to B. So you can split the integration 1 from here to here. So when you are going from here to here, your 10 ampere is captured. And again from here to here, another 10 ampere. So integration is nothing but summation, right? Again from here to here, one more loop. So whatever the number of loops are there, so the total enclosed current is nothing but N into I. So I is the current passing through that. So what it actually represents was, right now suppose if you take 4 turns, you are going to get it as a 40 ampere. So it doesn't mean that the 40 ampere current is flowing in the wire. No, the current passing through the wire is 10 ampere, but you are able to capture a magnetic field corresponding to 4 times of this. So that is what is that I enclosed it represents. So I can put the Maxwell equation like this. Integral H dot dl is equals to I enclosed. If it is having n number of windings, the number of N into I is the current flowing through the wire will be the I enclosed. So what it means, this 40 ampere whatever you have got is not flowing through the wire. Indeed, it says that the net magnetic field you are going to capture when you are integrating from A to B is equivalent to 4 times of the current. You got my point?
Yes, sir.
Somebody is asking, can you repeat why Ni it is? I told you, right? You are doing the integration. Integration is nothing but a summation. You can split the integration from here to here in terms of 4 line integrals. From here to here you do, and here to here, and here to here, here to here. So total how many number of loops are there, that many times you are making the loop. So for each loop you are going to carry one time I. So when you have n number of windings, you are going to have a n into I. But that doesn't represent the actual current passing through the wire. So I will put it in a simple word. So this is your 10 ampere and you are having 4 windings here, right? So this is equivalent to 40 ampere in a single loop. I hope this makes complete picture for you. Is it correct or not? Whatever the diagram I have seen. So what I mean to say, if you are trying to enclose the wire of 10 ampere current with a 4 number of windings, it is equivalent to 40 amperes of the current enclosed by the one loop itself. That's what it says. So what it says, integral h dot dl is equal to n into I. So in the first case, what you are going to get is the 40 amperes. So this 40 what is the meaning of this amperes law says? You are going to capture the 4 times of magnetic field. If you take one loop, you are capturing magnetic field corresponding to I. And if you take a 4 number of loops, your magnetic field is increased by n number of windings. And I hope this makes sense. So the same thing I was representing it in a virtual diagram. So if we have a 4 loops in a 10 ampere current is same as 40 amperes of the current in one loop. Is it clear for you?
So is this similar kind of logic used for the transformer as well?
Exactly. In transformers, why you are making so many number of windings, you tell me? Because when you are having any transformer, your inductance value has to be higher, right?
Yes, sir.
Yeah. When your inductance has to be high means what you need to do? That transformer should be able to store more magnetic field, right? The inductance can be increased by increasing the current. The first thing is that. Okay. See, suppose I have increased the current randomly, but sometimes what will happen? The core will saturate. Suppose you have taken, let me say, you have taken a solenoid, right? The core is able to support up to 10 amperes current only. In this case, I cannot increase the current. So, what is there in your hand to increase the inductance?
Increase the number n. It is
Yes.
turn.
Why you are making more number of windings in case of inductor was by making more number of windings, you are able to capture more magnetic flux. So it can be two ways. Either you can increase the current or else you can increase the number of windings. You can increase the current means it's well and good. Your magnetic field is straight away proportional to current. It is very good. There is no problem at all. Even if you increase the number of windings also, you are going to increase the magnetic fields, right? Using your Ampere's law. That's what it says. So either you can increase the current or you can increase the number of windings. That's what required to capture the more magnetic field. So if I say solenoid is having more inductance means it is storing the more magnetic field. So the magnetic field can be possible either by increasing the number of windings or number of current. So it's easy to increase the number of windings, right? So I hope this is clear, right?
Yes, sir.
We'll go back to the same presentation. So finally what it says, when you are doing the line integral of magnetic field intensity, this will be equal to I into enclose, I enclose. So for n turns around a wire, the total enclosed current will be n into the current flowing through that. Okay. Now the same thing, I will try to put it in a vector notation. So since the line is closed, you can apply the Stokes theorem. So the line integral is converted to surface integral using the curl operator. So whatever the line integral is there, I was writing in a surface integral using curl of H into ds is equal to, so consider one loop. So if it is one loop, I can straight away say it is a current I itself. So just now we have seen in the current distribution, the current I can also be written as a double integral J dot ds in terms of volumetric current. So if you remember, I have given this equation. I is equal to integral K into delta Y, or it can be double integral J into delta S. So it depends on the type of distribution. So this time I have written the current distribution in terms of volumetric because it is easier to compare these two now. So when you compare these two equations, now I will get the circulation of magnetic field in the flux density is equal to J. So the curl of H is equals to J. Is it clear? So now I will write the Maxwell's equation clearly. Everything, line integral form as well as the vector form, both will write. So the first thing, when you consider electric field and magnetic field in integral form, if you write, so there the first equation was integral E dot dl is equals to 0. And in here, Ampere's law, what is that Ampere's law says? The line integral of magnetic field intensity is equal to the current which is enclosed. Similarly, what is the Gauss law there? There it says double integral d dot ds is equal to the charge which is enclosed. And here what it says, when the surface is closed, the magnetic flux leaving the surface is exactly 0. This is in integral form. Now, if you write the same equation in vector form, so what is that there I have given? The curl of electric field intensity is 0, whereas the curl of magnetic field intensity here is equal to the current density J. Just now we seen that. And the Gauss law in point form, you can say the divergence of the flux density is equal to rho v. And similarly, when you are converting it here, the divergence of magnetic flux density is always 0. So this is the summary of all the Maxwell's equation corresponding to static fields. So any questions you can discuss before going to the problems. So quickly, if you can ask any questions, or else we can go to the problems. Okay, shall I start the problem then? Yeah. So today actually what is my plan was, you try to solve the problem. If you are not able to do, I will explain it here. That is a motto here, because if I will write it on the board, it's not going to help you, right? First you can try it and reply the answers in the chat box. So based on that, I will discuss, right? So first see this question and you can read it. There are two infinitely long wires carrying currents are shown as in the figure below. So one wire is located in the YZ plane and parallel to y-axis. So you can see here, this is a wire located in YZ plane and parallel to y-axis, fine. And the other one is located in the XY plane and parallel to y-axis. So this is located in XY plane and parallel to x-axis. So which component of the resulting magnetic fields are non-zero at origin? Which means that this is your observer point. So you have to define what will be the direction of magnetic field here. So my suggestion was, all of you Start with the Fleming right hand rule and tell me the answer. So let me say this is first element and this is your second element. So apply the Fleming right hand principle and tell me, because of current element 1, what will be the magnetic field direction here? And similarly, what will be the magnetic field because of second wire? All of you start with the right hand, Fleming's right hand, because I am not able to represent here. You do it that one.
Sir, the other wire is parallel to the x-axis, no?
Correct, correct. So first you tell me the magnetic field due to the first wire. All of you, what you need to do, you start with your right hand and make sure that right hand thumb should parallel to y-axis. So right hand thumb is parallel to the y-axis. So what is the circular movement of all other fingers when it is coming towards the origin? Is it into the paper or outside the paper? Into the paper. Into the paper means, can you tell me what is the specific direction it is? Because if you see here, this is located in YZ plane, right? So which is coming outside of the paper is positive X. Which is going inside of the paper is negative X, isn't it? Good, negative X. So if you start with your right hand, which means that the magnetic field is resulted in the negative X direction. Very good. So do the same thing for second also. Right now, you make your thumb in the same direction of X. And what is the movement of all other finger shows? Negative Z axis for second. Very good. Good. So when you make your thumb in the same direction of X, even the locus of other fingers also pointing inside. And see, right now, since that is a XY plane now, so positive Z will be outside and negative Z will be inside. So since your fingers are pointing into the board, into the plane of the paper, the resultant value will be negative AZ. So the component of the magnetic field which are non-zero at the origin is nothing but one is X component and Z component. So this is the answer. So let us do it using our conventional method also. The second method, what is the second method? The direction of magnetic field is equal to current into radial direction. So remember, radial means always going away from the source. So you should keep it in mind this point. Radial direction means moving from source to observer. Okay. Now you consider the first current element. So if you consider the first current element, the current is flowing along y-axis. So the current direction will be y. Can you tell me what is the radial direction by considering the first source? I told you, radial means source to observer. So source is this and observer is this. So when you are moving from source to observer, which direction you are moving? Good. Specifically speaking, it is a negative Z, right? AY cross minus AZ. So that results in a component of negative X, right? The same thing, whatever you got here also. So similarly, when you take the second wire, the current is flowing in the X direction. So current direction is X. Radial direction means this is source and this is observer. So you are moving in this way. Towards the origin means you are moving against 2y. So that is nothing but minus AY cap. So the resultant value will be minus AZ cap. So the same thing you got with the right hand rule. So is it clear for everyone, this question? Yeah, I will go to the next one. See this question. So there is a magnetic field in free space that is measured to be, he has given some equation. So what current distribution leads to this field? So if you see the options, all the options are given in terms of current density. And how to find the current density when you know the magnetic flux density? So can anybody say the approach? So don't reply in the chat box, you can speak out here so that everyone can listen. So the options are given in terms of current density. How to find out the current density when you know the magnetic flux density? At least 1 or 2 persons can give an approach for that. How to do that? No idea.
Sir, del cross H is equal to J.
Yeah.
And again H is mu B by mu.
Good.
Can we use?
Very good. Yes, that's it. You can apply the Ampere's law. That's it. Ampere's law in a vector form. You know that what is the Maxwell equation you have seen just now? The curl of magnetic flux field intensity is equal to J. So to find out the current density, you need to take the curl of H, right? So you know that, which means J can be curl of the magnetic flux field intensity can also be written in terms of B by mu. Since it is free space, I have taken it as mu naught because you know the relation B is equal to mu into H. So H can be written as B by mu. So it is simply, so the value of J is nothing but 1 by mu naught times the curl of B. So first everybody find the curl of this vector and divide with mu naught. And I hope by this time you would have been familiar with the divergence and curl, all these things. So you can find the curl of that vector. So AX, AY and AZ. And the second row will be the differentials, dou by dou X, dou by dou Y, dou by dou Z. And the third row will be the coefficients. So what is the coefficient of Ax here? That will be minus y by x square plus y square. And y coefficient will be x by x square plus y square. And there is no z coefficient. So you can simplify and tell me the answer. You take time, no problem, but tell me the answer. So after solving, you can post the answer in the group. Which option is that? So anybody done? Answer is C. So you are getting the current density as 0. Good. So others also is solved. And I will straight away say, since AX term, if you are calculating, you will get 0. You would have been verified by this time. And AY coefficient also will get 0. And if you see the AZ coefficient, so what will happen? And you will get dou by dou X of this one. So which is of U by V rule. You know that V into U dash minus U into V dash by V square. You apply that formula. So we'll get X square plus Y square minus X into 2X divided by X square plus Y square whole square. Minus dou by dou y of this one is also U by V. So that minus and this minus I can written it as plus. So you are going to get x square plus y square minus y into 2y divided by x square plus y square whole square. So you can simplify this. You are going to get this is your y square minus x square and this is x square minus y square. So the numerator is going to get cancelled. So I was leaving it to you only. You take time and do it. So you are going to get the value will be 0. So denominator is same and just your numerator part get cancelled. You can see that. So the answer will be here 0. So and I hope I can skip this, right? You will do it, right? I will go ahead. So you will do or you want me to do again clearly here? Clear. Okay. I will go to the next question then. Yeah, see that? So there is a magnetic flux density at a point is given by, so this is a magnetic flux density in Weber per meter square. Then you need to find this constant K. So how to do that? So we already know if it is any magnetic field, the divergence of the magnetic field vector will be always 0. You can apply that. You will get the answer. So when you take the divergence of B, you can say, since it is in rectangular, I told you the shortcut. So differentiate the AX coefficient with respect to X. So that will be 4. And differentiate the AY coefficient with respect to Y. Sorry, actually there is one term which is missing here. This will be 2KY. You can correct it. So the actual vector is like this, 4x AX cap plus 2KY AY cap plus 8 AZ cap. You can correct that question. So the divergence of this will become 4 plus here it will be 2K and differentiation constant is 0. So your divergence of magnetic flux will be 0. So correct, 2K will be minus 4 and K is equal to minus 2.
In exam, they will mention B or H like this.
Yeah, but even though they didn't mention, you can see the units. Definitely they are going to mention the units.
Okay.
Sometimes they will not give the sometimes they will say the magnetic field vector is given by so and so, and based on the units you have to expect.
Okay, if they give B or H, it will be easy.
Units definitely they will be given, but they will not give it is B or H most of the times.
Okay.
Since this is the first class, for your understanding, I was giving you. But in most of the exam, they will say that the magnetic field vector they will call. Whether it is flux density or field intensity, you need to have the knowledge on units.
Yes, sir.
Okay, right. So see the next one. So for the current density here, so here also I told you, sometimes they will mention the constant as K, but it will be up to them. But based on the units only, how to expect. So can you tell me what is the type of current distribution this one then? What is the type of distribution of current here? Is it line current, surface current or volumetric current?
Volumetric.
Yeah, volumetric, because even though forget about this, you see the unit of this, ampere per meter square is a volumetric current. So you know the current density distribution, he is asking to find out the current through a cylindrical surface having rho is equal to 2 and Z will vary from 1 to 5. So this let me do. So in case of a volumetric current we have seen, the current is basically the current density multiplied with the area. That's it. Now this question you have to answer me, since the current is lies in the direction of rho, right? What should be the surface direction then in that case? The surface is what plane? So I told you when you are taking the surface, you should consider a surface which is perpendicular to the current density. So in this case, the current density lies in the rho direction. So this surface you have to consider, so which means that phi and z will be varying. Good. So people are right. Phi and z planes are combined. Yes. So when you consider this surface, you consider a surface such that there is a variation and there is a z variation in terms of cylindrical. So you can define that I is equal to, sorry. So I is equal to double integral j dot ds. So j value already you know 10z sine square phi into aero cap. Can you tell me the surface area where phi is changing and z is changing? So when phi is changing, the variation will be rho into d phi. And when z is changing, the variation will be 1 into dz. And what is the direction of this surface? Reply here. What is the direction of this surface?
Arrow, sir. Arrow.
Good, correct. That's it. So if current density and the surface area both are in the same direction, then only we'll have a finite current. That actually makes sense, right? So now you take the dot product. I is equal to double integral. So arrow dot arrow, you forget about that. So you will get 10 rho z sine square phi into d phi into dz. So rho also you take it constant because integration is with respect to phi and z. So 10 into, so rho value already given, constant value it is 2, and integration of z dz into integration of sine square phi d phi. So you can do the integration right now. So this will be 20 into, so integration of z will be z square by 2. So 1 by 2 into z square, and here he given z varies from 1 to 5. And you know that phi limits for a complete cylinder, it will be 0 to 2 pi. So in the question, he's talking about a cylinder, right? So which means the integration will be from 0 to 2 pi. So what is the value of integration of 0 to 2 pi sine square phi? What is the value of that? You can reply. Pi, correct. So not only this one, you try to remember one shortcut. When you are integrating sine power n theta, when you are integrating sine power n theta over the whole period, so you know that sine theta total period will be 2 pi radians. So when you are integrating sine power n theta over the whole period, you are going to get the answer as half of the total duration. So 1 by 2 times of the total period. Or otherwise you can do it in a different methods also. You can say sine square phi is equal to 1 minus cos 2 phi by 2. That you can do. But instead of that, you try to remember this formula. So if it is sine cube or sine power 4 or whatever it might be, if you are integrating over the whole time period, the answer will be half of the time period. So you can apply that formula. So the answer will be 1 by 2 times of 2 pi. That's it. So you can simplify what you are going to get. So 10 into, and this 2 gets cancelled, and this is 24 minus 4. So 24 into pi. So you are going to get 240 amperes. This is the current. Clear? Shall I go ahead now? Yeah. This part I was leaving it to you, and you can do and tell me the answer. So determine the current density J associated with the magnetic fields. So you need to find out the current density J in ampere per meter square. If you want, you can write down that. Associated with the magnetic fields. So it's right away the curl of that vector. So we know that to find out the current density, it is straight away the curl of the magnetic field intensity. So find the curl of that vector and tell me the answers. And do it, and you can share the answer in group. So here also simultaneously I will be writing and you can go through that. The first one is correct, minus 2 A by cap. Yes, I hope everybody verified. So the answer is ampere per meter square. Do the same thing for second one. So when you are writing the second one, be careful about the scaling factors. So the scaling factor is 1 by rho. And the first row will be same thing, A rho cap multiply with the scaling factors, rho into A5 into AZ. Rho 1 is the scaling factor. You should remember that. And the third row will, second row will be dou by dou rho, dou by dou phi, dou by dou Z. And the third row will be multiply the coefficients with the scaling factors. So 6 rho into 1 and 2 rho into rho, that will be 2 rho square. And last one will be 5 into 1. You can simplify that. So when it is cylindrical or spherical, be careful with the scaling factor. 1 by rho, A rho cap into. You can verify, you also simultaneously do and cross check the answer. So I think you are going to get 4 into AZ cap. So confirm. Yeah. Okay, then we will go to the next question then. Next one. So there is a current density which is given. Again, this is a volumetric current, and you need to pass the current through a hemispherical shell of radius 20 centimeter. So first of all, I want to characterize what do you mean by hemispherical shell. See, when you have a complete sphere, something like this, spherical shell means it is cut something like this in the horizontally. So this particular part is nothing but your hemisphere. So consider your hemisphere. What is the value of R here right now? He given R is nothing but 20 centimeter. And when you consider for hemisphere, what is the total range of phi it can happen? So when you move on the upper half, that means each half represents one hemisphere. So when you move on the hemisphere, what is the change in phi that will happen? Imagine that you had a complete sphere and you cut it horizontally. What will be the total range of will happen? Phi. It is pi. Somebody is telling 0 to pi. No. 0 to 2 pi. Correct. You see here, you take a sphere and consider this is your z-axis, right? The axis of the sphere is z-axis. The moment once you cut horizontally, you see the base will be a complete circle or not? The moment once you cut off and look at the base part, is it going to make a complete circle or not? You are getting my point? You cut the sphere horizontally and look into the base. So the base is going to make a complete circle or not? Azimuthal plane. Yes or no? Yes, correct. So the phi is going to make a complete 360 degrees in the azimuthal plane. What happened in a elevation plane? So the moment once you cut it horizontally, this portion is isolated. So I told you in case of an elevation plane, when you are moving from here to here, there will be 180 degrees. So since you cut it up to here itself, so phi will ranges from 0 to pi by 2, right? The ideal value of phi is basically ranges from 0 to 180 degrees. And since half part is already gone, so which means that from here to here, if it is here, phi is 0. And if it is here, phi is 90. So, sorry, theta. I'm sorry, it is theta. So theta is varying from 0 to pi by 2. Now, can you do the integration right now? So the current is equal to double integral j dot ds. Right now, this surface is having a constant value of r, and theta is varying and phi is varying. So how to write the surface area vector in that case? The change in theta will be r into d theta, and change in phi will be r sin theta into d phi. And the direction will be here, since r is constant, direction will be r cap. So what is the dot product right now? J dot ds is equal to, sorry, j dot ds is equal to, so in the given expression j, your a theta term can be neglected, because when you take j dot ds, one component is ar dot ar, that you will get a finite value. So when you take a theta dot ar, that will be 0. So the second component can be neglected because the dot product will be always 0. So because both are perpendicular, so cos 90 will be 0. So your j dot ds right away will become 1 by r cube into 2 cos theta into ar dot ar is 1, and this one if you do it, you will get r square sin theta d theta d phi. That's it. So what is the value you will get? So this is equal to 1 by r into 2 sin theta cos theta. You can write it as sin 2 theta, right? Into d theta into d phi. So now you can integrate this to get the current. So to get the current, so 1 by r is a constant, to take it outside. So 1 by 20 into 10 power minus 2. Okay. Integration of sin 2 theta d theta. So theta values you have to be careful, that is from 0 to pi by 2. And phi value will be straight away, I can say 2 pi. So please simplify and tell me the answer.
So,
Yeah. Yes.
could you just explain again that how you got that the limit of phi and theta?
Okay. See here, when you consider any sphere, hemispherical shell means you have been cutted it horizontally. That means you
Yes,
take a
sir.
complete sphere and you cut the half portion. So each half represents a hemisphere, right?
Yes, sir.
Now, when you cut it horizontally, see, you had a complete sphere and you cut it horizontally. And look at the base plane. So when you look at the base plane, is it forming a complete circle or not? Phi means the angle measured in a azimuthal plane. Is the definition clear for phi, first of all?
Yes, sir.
So when you look at the horizontal movement, when you make only one hemisphere, okay, you take a complete sphere and cut it half. That means one part you completely remove it and take it only part and look at the base. So when you look at the base, are you able to get a complete circle or not?
Okay, okay. Yes, sir.
You got my point or not? See, this is
Yes.
your complete, and you are going to get a complete circle like this, right? This is
Yes,
how.
sir. Yes, sir.
So you are going to see the complete angle in the azimuthal plane.
Okay,
So
okay.
complete angle in the azimuthal plane means 360 degrees.
Okay, sir. Yeah.
And what will happen in a vertical plane right now? Because half portion you already cut it, means your theta is varying from here to here up to this. If you have a full sphere, it would have been completed like this, right?
Yes, sir.
But
Okay,
since you
sir.
have only half sphere, That means theta is varying from here 0 and up to here only. So when
Okay,
theta
sir.
is 0 here, and theta value will be pi by 2 here, right?
Yes, sir. Clear. Thank you, sir.
Yeah, that is from 0 to pi by 2. Okay, anybody done? What is the answer here? Integration. So I is equal to 1 by 20 into 10 power minus 2. So integration of sine 2 theta will be, so 1 by 2 into cos 2 theta, right? Of course, this is minus from 0 to pi by 2 into 2 pi. You can simplify that. So 10 pi, 1% is minus 10 pi. Cross check that. So here if you substitute the upper limit, this will be cos pi. Here you will get minus 1, minus 1. So minus 2 you are going to get. So this is going to become plus 2. So this portion fully get cancelled. And you are going to get 5 into 2 pi plus 10 pi it is. Right? You cross check it. It is going to be plus 10 pi. Yeah. You can do this part, not a problem afterwards. And the last question we will see right now. So you can do the calculation, I hope. It took sine integration as plus cos. Okay, no problem. Okay, do the last problem. So find the current enclosed in the following loops. So this is a loop I was considering, and in that there are some currents are there. So 10 ampere is into the plane and 20 ampere is outside the plane. So what is the total current enclosed in this? So you can tell me that. So this kind of problems are very important in gate. See, when you look at A, I will tell you one simple experiment. All of you start with your right hand and make sure that the locus of other fingers, that means other than thumb, you should match it to the loop direction. So right now the loop is in clockwise or anti-clockwise? It is in clockwise, right? So the moment all of you try by matching all other fingers except the thumb matching to clockwise. In that case, your thumb is pointing into the plane or out of the plane, you tell me. So when you see the first problem, all of you start with your right hand and ensure that other than thumb should represent the clockwise movement. So if you are able to arrange in that fashion, the thumb is representing into the plane or outside the plane. Into the plane. Very good. Yes. The moment once you put thumb into the plane, you can see here all other fingers are matching to the clockwise. So what is the meaning of that? Since the magnetic field is in clockwise direction, whichever the current is into the plane, that will be the positive current. So which means that since the loop is clockwise, so your thumb is pointing inside. So since the thumb is pointing inside, so this will be the 10 ampere is one current, which is a positive number, plus, and this 20 ampere represents outside. So the net current will be minus 20. Because using Ampere's law, what it says, in a closed line integral of magnetic field, if we do the integration, that will be the total current enclosed. Right now, in this particular loop, there are two currents which is enclosed. So which one to consider positive and which one to consider negative is basically depends on your right hand rule. So when you match the thumb inside, so it is matching to the loop. So whichever the current shows into the plane, you should consider it as a positive, and whichever the current showing outside the plane, you should consider it as a negative. So that is the reason why the answer is 10 ampere plus minus 20. You are going to get minus 10 amperes. So the same thing, can you do it for the second one and tell me? Second question. So this time your loop is anti-clockwise. So all of you start with your right hand and make sure that other than thumb should be anti-clockwise. So the thumb is pointing which direction? So other than thumb, if you are arranging your fingers to be anti-clockwise, so the thumb is pointing outside, right? So since the thumb is pointing outside, what is the meaning? Whichever is represents dot. Dot represents outside. You should remember the notation. And into means into the plane. So since the loop is anti-clockwise, so the thumb is pointing outside here. So whichever is outside, you consider it as a positive current. So one current will be plus 10 and this into current you consider it as a minus 20. So that will be minus 10. So is it clear? So is the concept clear till now? Whatever I have discussed? Yeah. So if you want one more exercise, I will give you. This you try to do it and tell me the answer. If possible now you can tell, or otherwise you can tell in the next class. Not a problem. Just for your knowledge sake, I was giving one more experiment something. So there are 3 current carrying wires like this. Yeah. Now there are 3 current carrying wires like this. The moment once you are starting from this and you are going in this particular loop, okay, and you are coming back. So the moment once you are making this movement, what is the total enclosed current? So in this particular loop, whatever I have shown here, when you are moving in this particular loop, what will be the net total current? I want to find the answer. So will you tell now or next class? You can reply here now only. You want to do it now or in the next class? Now only want to do. That's a good spirit, right? Yeah. So the answer is going to be 2. No, cross check. No, -2 is also wrong. 0. So all combination tell now. 3 plus 2 plus 1, 3 minus 2 plus 1, like that. So how many combination will come? 6? No. Okay. So let me explain you. So consider this is your loop 1 up to here, only this portion. So when you see the loop 1, is the direction of the flux and the current both are matching or different? If it is matching means you can take +3. If it is mismatching means you take -3, right? So when you go in a loop 1 is going in a clockwise direction, right? So loop 1, I means this portion. So when you are taking a loop 1, somebody is saying matching. No, you see here. So when you take the loop 1, it is a clockwise. Now start with your right hand So other than the thumb, you make it in a clockwise direction. Yeah, correct. The thumb is matching. Thumb is downwards or upwards in that case. When you are matching your fingers in a clockwise direction, the thumb is pointing down or up. So down, right? So the current whatever I have given is also down. So it is exactly loop 1 is +3. Yeah, Ambrish is correct answer. 6 is correct answer. Yeah. L2. In loop 2, what will be the value? Loop 2 is anti-clockwise. So when the loop is anti-clockwise, match all other fingers in an anti-clockwise manner. So the thumb is pointing up or down in loop 2. So when you match the fingers in anti-clockwise, the thumb is pointing in which direction? Up direction, correct? So whatever the current I have given is also up direction. So that is also matching, +2. And finally loop 3. Loop 3 already you've seen, right? Loop 3 is clockwise, so the thumb has to point downwards, same as loop 1. So loop 3 is clockwise, you can see here. This is a clockwise notation. So when you see the clockwise and thumb is pointing downwards in that case, and whatever the current I have given is also 1. Correct, good. So the total current will be 3 plus 2 plus 1. So that will be the 6 amperes. Correct. And I hope you understood all the concepts now. So my next class is there on the Saturday at, I think, what is the time? Saturday 5:30, yeah? Correct time? I think Saturday it was there at 5:30 it seems, yes. We had 5:30 to 7:30 class, yes. So before coming to the next class, you try to revise all the concepts that we have discussed today in magnetostatics. So immediately I'm going to share you the presentations and you can go through it and learn the concept and solve the problems and be prepared for the next class. Okay. Okay, then you can sign off now, right now. Thank you very much.
Thank you, sir.
Right.